Alright, so today we're going to be talking about continuity. Continuity is mostly about definitions, and it's pretty intuitive, especially compared to limits, I guess. So let's just get to it. So, continuity is used to describe functions, and it's really just what your intuition would say. A function is continuous if, I guess, like a crude definition would just be like if you could draw the function without picking up your pencil or something, it's continuous. But obviously, let's get to like a more mathematical definition. So, the definition. A function y is equal to f of x is continuous. And we're going to split it into inner points and outer points. First we'll talk about inner points. It's continuous at an inner point C if limit as x tends to C of f of x is equal to f of c. So basically it's saying if the limit of that point is equal to the value of the function at the point, then it's continuous at point C. For endpoints, and obviously C has to be in the domain of f, right? For endpoints, a function y is equal to f of x is continuous at a left-hand point, left endpoint, if limit as x tends to a from the positive end of f of x is equal to f of a, left end point A, and at a right end point B if limit as x tends to b from the left side of f of x is equal to f of b. Basically it's saying if the limit of the function, like the right or left side limit, is the value of the function at the point, then it's continuous at those endpoints. Now, these definitions might be hard to swallow, so let's just, draw it out. Right here, I have a function that I'm going to draw out as the coordinate axis, and this is what the function looks like. This is a right endpoint, and this is a left endpoint. And then we'll call this B. We'll call this A. Let's just say this value is some y1. This is some y2. And then we have some intermediate y3. And then this is some point C. Right? So we clearly see that the limit as x tends to a from the positive side of this function f of x, so let's call this as f, is equal to y1, right? And similarly, limit as x tends to b from the left side of f of x is equal to y2. And limit as x tends to c of f of x is equal to y3. And because all these match, we see that this function is continuous at these points. Now, let's go on to examples of non-continuous functions. So a very common example of a non-continuous function is a step function, right? So this is how a step function usually looks. And we see here that a function would be discontinuous at like this point B because the limit at this point B is not really defined, right? So it would be discontinuous at this point. Now, this brings us to classification of types of discontinuity. And this is just mostly like terminology. I don't think it's really too important, but I mean, for completeness, we'll show it. So let's say we have a function like this, right? It's undefined at this point, or let's say it's not defined here, but it's defined here at point B. We call this a removable discontinuity. Because at point B, if we were to instead sort of define, if we were to instead say f of y where, f of b where equal to y, instead of this value z, then it would be a continuous function. Basically it's saying if we can add in like a point, like in this example, we can make it a continuous function. So this is a removable discontinuity. Now, going back to our example of a step function, when the function sort of jumps, right, so we'll see how it's jumping from this like value y1 to this value y2, we call it a jump discontinuity. And we have a jump discontinuity at point B. Next. Oh, that's bad. Oh my god. Okay. Let's say we have a rational function, 1 over, or let's just do 1 over x squared, so I don't have to. So this is y is equal to 1 over x squared. Basically, we know at point 0, the limit as x tends to 0 is infinity, right? Here we call this an infinite discontinuity. You know what, let me actually put this in red. So this is an infinite discontinuity. Basically, whatever you have a discontinuity where either side goes towards like an infinite value, it's an infinite discontinuity. And then for a final one, this is a very rare example. So y is equal to sine 1 over x. Now, as we head towards 0, we see how like 1 over x will go towards like really large values. And you know how sine is a periodic function, so it will basically, like its period will start getting smaller and smaller because you're jumping values and you're moving really fast, so it looks something like this where it keeps going fast. But we can't really know what's happening at 0 because it's shifting way too fast. And so this discontinuity is known as the oscillating discontinuity. So this is oscillating discontinuity at x equals 0. Because it's oscillating so fast and the numbers start changing at such a high pace that we don't know what's happening at 0. So in summary, so in essence, there's a removable discontinuity, there's jump, there's oscillating, and there is infinite. So these are the different categories of discontinuities. So now let's get back to a continuous function, right? We have a definition. A function is continuous on an interval and this is if and only if it is continuous at every point in the interval. Now this is kind of obvious, right? Like a function was not going to be continuous if exists a point where you have a discontinuity, like the ones that we described over here. So what's like the importance of continuous functions? Like why do we care so much? Well, they give us some interesting properties. So we have some properties that are nice. Namely, if two functions f and g are continuous at point C, then these combinations are also continuous at point C. So f plus g, so sum f minus g, their difference, f times g, the product, k times f, a constant multiplied by f, and finally f divided by g, provided g of c is not equal to 0. I mean, so basically, when we have two functions that we know are continuous at the same point, we know like we can combine them in a way, and then we can also get a continuous function out of them. Now let's just use this property real quick. Show that the absolute value of x sine x over x squared plus 2 is continuous. So we can treat each part of these as different functions. So let's say x is a certain function, sine x is another function, and x squared plus 2 is another function. We know that x squared plus 2 is never equal to 0, right? Because it's always positive, right? We know x is defined for all values, right? From negative infinity to infinity, and so is sine x from negative infinity to infinity. And because all of these functions are defined from negative infinity to infinity, and the denominator is never 0, that means we can use these properties. So if we call x a function g, right? So g times sine x, which we'll call like f, is continuous at all points, and h, which is x squared over 2, which we'll call s squared over 2, is also continuous at all points. So that means this whole function is always continuous. Pretty easy, right? And now, the final part. This brings us to something called the intermediate value theorem. So, theorem, actually I'll just, the intermediate value theorem. So as a consequence of continuity, we have this intermediate value theorem, which states that a function y is equal to f of x that is continuous on some interval ab takes on every value between f of a and f of b. So, in other words, if c is less than or equal to f of b and greater than or equal to f of a, right, then, basically if c is between f of a and f of b, we will not necessarily know that f of a is greater than okay, let's just say if f of a is less than f of b and c is in between those, then there exists some f of x for x between b and a. Oops. Where f of x is equal to c. Let's just, I think, this theorem is pretty powerful. It just tells us that if you have two values, at endpoints, and we know their y values, or, their outputs, we have, and the function is continuous, all the intermediate values between them must be hit, right? And I think if he shows graphically, it will make more sense. So, let's say we have this function, right? It's like a random function. And we're given that this is b, point B, and this is point A, right? So this is y1, and this is y2, right? So we know that f of A is equal to y1, and f of B is equal to y2. And in this case, y2 is greater than y1, but it could be the other way around, right? So we know that there exists some x where x is less than b and x is greater than a, for which f of x is equal to some y, where y is less than or equal to y sub 2, and y is greater than or equal to y sub 1. And we can argue this by the IVT. Note that for this to work, we need the function to be continuous, right? Because if the function is continuous, you can draw it without, again, going back to the crude definition, you can draw out the graph or that traced by the function without picking up your pen, right? So intuitively, you have to cross through all the y values between the 2 points, right? Now, we can't, just as a note, we can't say for sure whether a value less than y1 will exist between the interval or not, because, I could have drawn out the function like this, and in that case, these values over here would not have existed, right? So, there might be trick questions like, can can a value y that's less than y1 exist? And I mean, it can, but it also cannot, right? So it's ambiguous. And that's basically it for continuity. It's pretty simple, right? It's pretty intuitive what you think about when someone asks you whether a function is continuous. And one of the biggest consequences of it is the intermediate value theorem, which is really important and it's pretty powerful.